This is a video explaining something in chemistry that we call LeChatelier's principle. And it says essentially that a system that is at equilibrium will stay at equilibrium forever. I wrote the definition down for our class session. So a system at equilibrium will stay at equilibrium forever until a stress is added to the system. Stresses will cause equilibrium to shift to relieve the stress. And so we're going to look at a few examples of adding a stress and shifting the equilibrium. Of course, if you need to copy that down, you can always stop the video. So now moving on to the little demonstration. This is a little lab that I would usually do as a demonstration in class, but we're not in class, so here we go.
In this lab, we will be studying a chemical reaction at equilibrium between two complex ion formations of cobalt.
Okay, I want you to notice that the cobalt here is surrounded by 1, 2, 3, 4, 5, 6 water molecules as illustrated over here. A couple of words will come up later. I'm just going to bring them up right now. These are not crucial to understanding the topic I'm trying to teach you. However, they're just nice words to know. The first one is ligand, L-I-G-A-N-D. So a ligand is something that provides a pair of electrons to usually a positively charged ion. So if you look at the picture of cobalt with a +2 charge, you remember each water molecule has 2 unshared pairs of electrons. And so those 6 molecules, each one of them is providing a pair of electrons to the cobalt ion. All right, ligand. And that doesn't come up immediately, it comes up in a little while. Notice that this color is pink and this color is blue. So when we actually get into the experiment, this side of the equation will be blue and this side will be pink. All right, now remember, equilibrium means that you're going back and forth between the two sides, so there's some of the stuff on the left and there's some of the stuff on the right, and there's always a mixture of it. If there's more of the blue, then that means that more of the COCO4, that means it'll be blue, and if there's more of the COH2O6, it'll be pink.
Because they form complex ions with water and or chloride ion that forces the reaction to go thermodynamically to...
This is called a complex ion, so as is that, which are groups of atoms together acting like an ion.
To the right, we should be able to see a nice blue collectance, and we will make more of the looking at these colors.
All right,
and
so
this is, I believe, a purple color, although I have a difficult time with colors.
All right, so what we have here is a example where this complex is favored, and another example over here where this complex is favored. I should mention to you that many of you have heard of cobalt blue. This is cobalt blue. So that's the ion that causes this blue color that you sometimes use in art class, cobalt blue. This is a more even mixture of the two colors. So you see that we have some pink and we have some blue, and together they make this purple color.
Of the equilibrium mixture of both. All right, so we're going to put out some test tubes here, and we're going to follow our procedure as follows. So here's our 4 test tubes. And again, right now we see the pink color, so all of these test tubes currently have a lot more of the reactants and products, as by the pink color favoring the copper complex with water. So we're going to begin our first test, and we're going to just add some hydrochloric acid into the first test tube. And doing so...
So hydrochloric acid is HCl. Hydrochloric acid is a molecular compound which really shouldn't dissociate, but it does because it is a strong acid. And we haven't talked about strong and weak acids yet, but strong acids act like ionic compounds. So you would end up with H plus and Cl minus. Now I want you to notice that, so what I'm really saying is you're not going to have any HCl in a bottle of hydrochloric acid. You're going to have hydrogen ions and chloride ions. Notice that those chloride ions are the same chloride ions that we have here. So in effect, when I add HCl, I'm increasing the chloride ions. When you increase the chloride ions, that will be a stress on equilibrium. Now remember, we said that the system will stay at equilibrium forever until a stress is added. So the stress causes the equilibrium to shift to relieve that stress. So we're going to see a shift in equilibrium when we add the HCl. Here it comes.
We see that thermodynamically there is a shift from this reaction going to the side with the blue.
So when we added the chloride ions, we made more of this blue stuff, which means that the shift was to the right. So this went up. I'm going to go ahead and circle the chloride. That was our initial stress. That went up, and this went up, the water. More water was formed, and there was less of the pink stuff. So equilibrium shifted to the right, creating more of the things that are on the right and less of the other thing is on the left. It's important also to note that when I increase this, there's some of what I added gets used, and so it goes up and then drops back down, not all the way to where it was before I added the chloride, but it will drop down some because some of the chloride will react. All right, moving on.
Compound. So now we're making a lot more cobalt chloride complex, the complex that is blue. Okay, and some calcium
Now
chloride.
we're going to add calcium chloride. That's the next stress. So calcium chloride, CaCl2, is a soluble ionic salt. So when you put it in solution, it's going to make calcium ions and chloride ions. And this doesn't exist anymore because when it dissolves, it does this. Remember, ionic things dissolve like this. Something like sugar, if that's solid and that goes into solution, the particles separate. So it's like if you have a bunch of little balls like this, little molecules, when you put them in solution, they separate from each other. But the little balls don't separate. Up here, this actually separates. Each little guy here becomes 3 parts in this case. So the actual formula unit separates. That does not happen with molecular things, except for strong acids. Okay, now moving on. So we added calcium chloride. In effect, isn't this chloride the same chlorides? So in our second example here, we're increasing chloride again, so predict what's going to happen. Here it goes.
And we'll add some more. And if you're looking at the
bottom,
the
see what's happening.
Shows a favored thermodynamic pathway, meaning we see a shift toward the blue side. We are making a lot more of that at some point.
All right, for this one, we're going to add water. So if you add water, there would be more water available. Let's put some lines in here so we can keep track of our trials. So if you add water, there would be more water available to combine with the cobalt, so that should make more of the pink stuff. So let's see if it works.
All right, so here comes test tube 1 again, which we can see is clearly favored, all right, with the blue compound. All right, and now we're going to add some water. All right, so now adding some Poland spring water, and again, this is not a, they didn't pay us any money to do this, but we're going to add some water, and by adding water, we can see definitely a shift.
So it immediately shifts to the left. Is that consistent with what we said? In the first 2 examples, we increased chloride and it shifted to the right. So these 2 lines have all the same kinds of changes. Increase that, shifts it to the right, this goes up, that goes up, this goes down, and a little bit of what I added reacts. Down here, equilibrium will shift. Since I got more water, we're going to be able to make more of this. So it shifts back to the left. And when it shifts to the left, you make more of the pink stuff, and that's why it turned pink. Okay, so that was our third scenario. Turn this sideways so I can write equations on it and not move off my camera. Here we go.
Toward the pink cobalt complex, and that pink cobalt complex is on the reactant side. These to split. Pretty cool stuff to go through. So test tube 3 here. Okay, we're going to add hydrochloric.
All right, in test tube 3, now we're adding hydrochloric acid. So we're going to shift it to the right. You should see more of the blue stuff forming.
Chloric acid, which we've done already before, and we're going to see a shift that favors the cobalt chloride complex. and you should know what that shift does. And now part of the same test now is we're going to add some silver nitrate. Notice the silver nitrate bottle, when it comes into play here, has it.
It's dark because silver nitrate is affected by light. It turns darker. Originally in photographic film, silver nitrate was used because it turns dark when subjected to light. All right, we need to talk a minute about the chemistry that's going to happen now. So when you add silver nitrate is going to break apart into silver ions and nitrate ions. So there really isn't any silver nitrate in this dark bottle. There are silver ions and nitrate ions. Well, neither one of these is in this equation at the top. So there's no silver, there's no nitrate, so there's nothing in common like there was in the first experiment we added HCl. That was common chloride. Calcium chloride had chlorides in common. Water was in the equation when I added water, but there is no silver or nitrate, so what must be happening? So I'm going to take you over here to the website and take a quick look at a sheet you're familiar with. Looks like this. And you'll remember in our solubility rules section that halides are soluble. Chlorine's a halogen. So chloride would be a halide. And it's soluble except for barium and mercury 1 and lead. So moving back over to our demo, not there, here. All right, we know that we add silver nitrate. The silver ions that are here should combine with the chloride ions and make a precipitate, which is silver chloride. So in effect, what I'm doing when I add silver nitrate is pulling out the chloride because this is solid, and if it's solid, it can't be dissolved in the water anymore. So I'm adding silver nitrate will remove chloride ions, remove them. All right, so here we go.
It is a dark bottle that prevents light from getting in too much because the silver ions are affected by the light. In any case, you see me adding some silver nitrate.
You can see the white precipitate forming down at the bottom of the test tube as he adds this. So the precipitate's forming, see the white cloudy stuff? And then look at what's happening down here. What color is it starting to change down at the bottom? Yeah, it's starting to turn pink. So by removing this, I'm pulling the equilibrium back in this direction. It's getting more and more pink.
Pink side. So I definitely see a pink color developing here as we add some silver nitrate. So
there's a close-up of the precipitate right there so you can see it in the bottom. Now we're going to use a water bath. We're going to have put test tube 4 in a hot water bath. And this water bath is about, you'll see on his thermometer, it's about, the whiteboard is 25, so he's going to put it in the water. It's going to be about 75. Okay, so now we're going to put a test tube in the water.
And in this test, we're going to put the test tube 4.
Okay, that's test tube 4 was pink. We're putting it in hot water. Okay, observe what happens.
In the hot bath, and we're going to see what kind of color change will happen.
Before we actually see the color change, although you might be able to see it beginning to happen now, let's do a quick summary of what we've seen up here. You notice that when I increased this, equilibrium went to the right. Increasing this, equilibrium went to the right. When I increased the water, it went to the left. In the fourth reaction, we had a decrease in chloride and it turned back pink. So that means that there was more of this, which means that equilibrium was shifting to make more pink. So these guys over here went down. All right, so we have enough here to get a basic relationship, and that is when I increase something, equilibrium goes away from that increase. It goes to the right when it was on the left side. When I increase something on the right side, it went to the left side. So we could say that equilibrium shifts, I'll write this down, kind of an important point, summary point. Equilibrium shifts away from an increase. And we can also see that when I decrease this, the equilibrium shifted toward that decrease. So I just use shifts toward a decrease. All right, so equilibrium shifts away from an increase and it shifts toward a decrease. Those are summary statements. Now we're going to look at this heat change. It's happening. This is in hot water. Remember, this is there's more of this right now because it's pink. It's in hot water.
Now we're changing the temperature here, so we're actually going to shift not so much the equilibrium. In truth, we're actually changing the equilibrium position to favor one side or the other.
Yeah, it's turning blue.
Adding heat. Oh, this is opposite.
And over a period of time here,
okay,
we see that it changes to dark blue, which is the cobalt blue color. All right, so equilibrium shifted toward the right when we put it in hot water. Let's take a look at what happens when we put it in cold water. Well, actually, let's evaluate. If it shifts to the right when we put it in hot water, does that mean that the reaction is endothermic or is it exothermic? Well, you know, we just said that equilibrium shifts away from an increase. And it shifted to the right. So if it shifts to the right and it shifts away from an increase, then we should know that heat is on the left side. So that would, this whole chemical reaction up here is what we would call an endothermic reaction. Quick review. Which one of these graphs applies? So this reaction would be that one, endothermic. Energy is on the left side. If that's true, when we put it in cold water, then this blue test tube should shift back to the left. Let's see if that's true, because it's going to shift toward the decrease. All right, here we go. We started
my warm solution back in.
There we go. Now we're putting in ice water.
To the ice bath, and you can probably guess what's going to happen here. And lowering the temperature, the reaction is going to shift to do the opposite, probably to increase the temperature. So it's going to favor whatever shift of equilibrium that favors.
All right, so we're consistent. If we were to decreasing this should cause it to shift to the left, in which case it would turn more pink, and poof, it is turning more pink. All right, that's a summary of shifting away from an increase and toward a decrease for both concentrations and temperature changes. Of course, there are other videos on this page you can watch. I wanted to take a minute to talk about pressure changes. Not that one, this one. So in this one I have nitrogen dioxide. One way to make this nitrogen dioxide is to mix nitric acid and copper. And when you mix nitric acid and copper, it creates a brown gas like this, or like this, same brown gas. Now, we'll watch this video and start at the beginning. This one's a shorter one.
We can show LeChatelier's effect of an equilibrium reaction here with this mixture of two gases. We've got brown nitrogen dioxide gas in equilibrium with clear N2O4 gas. When I squeeze the plunger and increase...
Okay, so what that equilibrium equation looks like is we've got this brown NO2 gas in equilibrium with dinitrogen tetroxide, N2O4, which is clear. To balance this chemical equation, we would need a 2 in front of that. All right, now what we're going to do is push the plunger in. I want you to watch what happens when we push the plunger in.
Increase the pressure. The first thing that happens is we get the intensification of color for physical reasons.
So what's happening is you squeeze the brown gas together, it's going to get more brown. But you notice that as you squeeze it together, watch again, it gets more brown, then it gets less brown. So it clears up. So what that means is, as we're shifting it, the equilibrium is moving from the NO2 to the clear side. So it gets more brown, but then it gets lighter. But it should stay dark if you're smashing the brown gas together. So the only explanation for the fact that it's getting lighter is that we are making more of the N2O4, which is a clear gas. One more time. Maybe one more time. Here it goes. Comes in, gets dark, now it gets lighter. All right, so bottom line for that is when you increase pressure, you've got to think about this relationship. If pressure goes up, volume goes down. Remember that equation from the gas law unit? So if pressure goes up, volume goes down. So if I increase the pressure, the volume should go down. Which side of this equation has less volume? You see how you got 2 moles on this side, only 1 mole on this side? So this side is going to be the side that occupies less volume. And we know that when you increase pressure, volume should go down. So therefore, in an equilibrium situation, an increase in pressure, so if pressure goes up, it favors the side with less moles. If pressure goes down, that will favor the side with more moles. All right, so one more time this little demonstration. We start, we're not going to start again, start over here. So we start out here, we increase the pressure, pushing down the volume, and it's going to get darker, and it should get darker, but then it lightens. Since it's getting lighter, we know that we are shifting the equilibrium to the right over here because there's less moles over here, so we're going clear, which implies that we're going to the side with less moles. All right, so for pressure, increasing pressure favors the side with less moles, decreasing the pressure favors the side with more moles. A little caveat, if you have equal numbers of moles, pressure won't have any effect. All right, so these are our summary statements. The equilibrium shifts away from an increase, and it shifts toward a decrease. And an increase in pressure for gases favors the side with less moles, and a decrease in pressure favors the side with more moles. All right, I think that'll summarize. That's the end of this little video. I put some practice problems on the website, and there also are other videos to watch related to this concept. And these, again, are the things that we covered in class today on May 4th, 2020.